So to begin, here is what we have for our new vocabulary. Okay, some of them are going to sound very familiar to you. Some of them are very new. First one is set builder notation. That comes from the first items that we did in pre-calculus this year, the sets, where we nominate a set and we determine what's all included within that set. Interval notation is another way to express the domain. It typically revolves around inequalities and parentheses and brackets. You'll see those. Your next one is function and function notation. When you're talking about a function, it is a special type of relation where each independent variable maps to one and only dependent variable. Okay, so in layman's terms, that's that each x value has one and only y value. So that when we are drawing a vertical line through our relation, if it meets our relation at only one point for each x value, that is considered to be a function. Okay, and that's not just limited to using whole numbers. You can go 4 and then 4.01 and then 4.02, 4.03. But if you were to draw a vertical line on each and every one of those, it would only touch your relation once. The independent variable is your x value. That's what you plug into your function, okay, to get your dependent variable, which is your y value. Okay, so independent is x, dependent is y. It's independent for x because x can stand by itself, whereas in order to get a y value, you have to plug in an x value. And then you have implied domain. Implied domain is almost exactly as it sounds. We assume that it's all real numbers unless we are told otherwise. Okay, and that's for just like y equals x squared or f of x is equal to x squared. So that would be called your implied domain as all real numbers. A piecewise defined function. These are the type of functions that are used to model real life situations when just one function doesn't really fit the bill. It doesn't map or match the data as best as it could. So mathematicians, they created these things called piecewise defined functions. And what they look like is they look like f of x is equal to x squared if x is less than 0. And then it might be f of x is equal to x plus 3 for the relevant domain of -1 to 5. Okay, so it's really multiple functions listed together to show one function. And you'll see those once we get to our word problems. They're not very hard. It's just like evaluating any other function. You just got to be very cognizant of what domain you're in. And then you have the relevant domain. The relevant domain is when they are all, when the book states the domain that it wants you to use in the given problem. Okay, so just make sure everybody can see the slides, everybody sees the vocabulary. And I shared the lecture assignment on Seesaw, correct? I hope. Yes, we're all good. Okay, so we're going to be back, and this is on page 8 of that PDF. Okay, so if we go next, the key concept that we're going to be using is real numbers. And you can tell from our little diagram here, real numbers encompasses all of these. This box represents real numbers. You have rationals, which are fractions that can be expressed in an ending decimal. Okay, so the example that they give you is 0.125, which is 1/8, -7/8 and 2/3. If it's completely repeating, or if it ends when you turn that fraction into a decimal, it is considered a rational number. Then you have your irrational numbers, like the square root of 3 or pi. Okay, those are decimals that will continue and continue and will never cease. They also don't repeat in any pattern that we can discern. Then you have your integers, which are whole numbers that are inclusive of negative numbers. And then you have your straight wholes, which are all of your positive numbers beginning with 0. And then you have your natural numbers, which are all positive, not inclusive of 0. But the key thing is you can see that real numbers encompasses all of these. Well, we learned from using complex numbers and the imaginary unit that we could take the square root of a -1, understand it's an imaginary unit, and we are only dealing in real numbers. Okay, the imaginary unit really only comes when we're trying to solve a quadratic equation or try to solve a parabola that doesn't touch the x-axis. Okay, because if it were to touch the x-axis, it would have a real number solution. So that brings us to our first example, and we're going to use set builder notation to describe how 2, 3, 4, 5, 6, and 7. We want to use set builder notation to give that domain. So the key thing when we're using set builder notation is we are going to name the set. Okay, you can name it as n, you can name it as x, you can name it as a. Okay, so the first thing that we do is we describe the set, and then we give the given properties. So for this case, we're looking at whole numbers that are between 2 and 7. Okay, we don't assume that it's gone farther because we have brackets. Okay, so we want to name the set, we're going to name the characteristics, and then we are going to say that our set is a given element of one of these, of either our whole numbers, integers, naturals, however it works. Okay, whichever fits best. So in this case, I'm going to describe my set as x, and my given characteristics are that x is between 2 and 7, and that x, so the set includes natural numbers greater than or equal to 0 and less than or equal to 7. So right there, they've given us what area we fall into. We fall in the natural numbers. And once again, we're greater than or equal to 2, and we are less than or equal to 7. So our answer and our set is x. 2 is x is greater than or equal to 2, x is less than or equal to 7, and x is an element of the natural numbers. So you can see where n comes from our little diagram on the last slide. And our answer would be stated just as that. Okay, and we assume that it's naturals because we're not including any negative numbers. There's no 0. And when we're using set builder notation, we really want to start from the center and work out. Okay, so if we go back, you can see that natural numbers is a part of wholes, which is a part of integers, which is a part of rational numbers. Okay, could we have said that x is greater than or equal to 2, less than or equal to 7, and is a part of rationals? Yes, that's true, but then you're encompassing more numbers than what's given in our set. So we really want to be accurate as to where these fall. Okay, so that's why they chose natural numbers, because there wasn't an element of 0. All of our numbers were positive. Okay, so we wouldn't have called them wholes because that encompasses zeros. We wouldn't have called them integers because that encompasses negative numbers. They're not irrational because they're all whole numbers. They are rational, but rationals also include all of the fractions as well. So we really want to narrow down what set we say that this involves to. Okay, so that's the reasoning behind them stopping at just natural numbers rather than expanding it to wholes, expanding it to integers. Okay. So our next example of using set builder notation, it says describe x is greater than -17 using set builder notation. So the first thing that we want to do is that the set includes all real numbers greater than -17. Okay, the implied domain is all real numbers. So x is greater than -17, and x is an element of real numbers. Okay, we had to use real numbers in this one because it not only encompasses negative numbers, which would encompass integers, it encompasses our irrational numbers and all of our rationals, which includes our whole and natural numbers. So really, to describe this set the best we could, we have to say that it is all real numbers. Okay, this one's a little bit trickier because it says describe all multiples of 7 using set builder notation. So it says that this set includes all integers that are multiples of 7. So that is inclusive of negative numbers. But the really difficult part is, how do we describe multiples of 7? So this is going to include us associating a variable as well. Okay, so we want to say that it's x times 7n, or x is equal to 7n, where n is an element of our integers. Just like that. So you can see that we're only including whatever is multiplied by 7. So that's where that 7n comes from. And n is an element of integers, and that is going to act as our answer as well. So you can see set builder notation is pretty easy. You're mainly describing items. Okay, so describe 6, 7, 8, 9, 10, and you can see that the 3 dots means that it continues, and it's using set builder notation. So looking at our set, we're looking at numbers that are greater than 6, and 6 is a part of our set. So x is less than or equal to 7. That's not going to work because you can see in our set itself we have 8, 9, and 10, which are greater than 7. Answer B, x is greater than 6, but you can see they don't have the greater than, so that doesn't encompass 6, so that's not going to work for us at all. And then you have D, x is greater than 6, which is true in this case, but it also states that x is less than or equal to 10. Okay, so D, it kind of limits it, but with our 3 dots there, we know our pattern is going to continue. So in this case, our answer would be C, x is greater than or equal to 6, and x is a set of natural numbers. Okay, so then that brings us to interval notation. Interval notation is another way to describe a domain, but it is centered around using inequalities, and we're going to use a series of brackets and parentheses to help describe us. So this table occurs on page 5 of your book. Okay, and I want to look at bounded intervals first. Okay, that's where the inequality A is less than or equal to x, and x is less than or equal to b. So you can see in interval notation, whenever we have less than or equal to, we use a bracket. Okay, whenever we are just saying that x is greater than or less than, we're going to use a parenthesis like they do in inequality number 2, where a is less than x and x is less than b. Okay, the third inequality is a is less than or equal to x, so that causes us to use a bracket next to a. What page? It's on page 5, Rosalind. It's on page 5 in your McGraw-Hill book. It's right there at the top. And I'm going to leave this up for a couple minutes. That way you guys can write it down. So A is less than or equal to X, which is less than B. So you can see we have a bracket next to A saying that, yes, that number is encompassed. But we're going to have a parentheses next to B saying that that number is not encompassed. Okay, and then we have A is less than X, which is less than or equal to B. So you can see we have a parenthesis next to A, and we have a bracket next to B. And I can zoom in just a little bit more. That way you guys might be able to see it a little better, make it a little bigger. Okay, so those are your bounded intervals. Once again, we use a bracket when it's less than or equal to, and we use a parenthesis when it is just stated as less than. So the bracket means that it's encompassed. The parenthesis means that it's not. Okay, for your unbounded intervals, these always encompass an element of positive infinity and negative infinity, right? Because if it didn't, it would be a bounded interval. If we allow it to go on to infinity each and every time, we know that we continue and we continue until we hit the highest number imaginable. So our inequality is x is greater than or equal to a. We would describe that as a bracket next to a and a parenthesis next to infinity. We will always have a parenthesis next to infinity. That's because infinity is used to just describe the highest number that you can imagine or the lowest number that you can imagine. So on the next one, x is less than or equal to a. You can see that we have an unbounded interval at negative infinity all the way up until a. Okay, the low number goes on the left, the high number goes on the right. So if x is just greater than a, we have unbounded at a, showing that a is not inclusive because our inequality states that it's not. And we have to have unbounded next to infinity, meaning that it's going to be every number from a.1 on. Now we have x is less than a, so we begin with a negative infinity and a parenthesis, and then we have a with a parenthesis, once again showing that it is not included in that interval. And then our inequality for the last one would be pretty easily described as all real numbers. It goes from negative infinity is less than x, which is less than positive infinity. So that's meaning that x is any number between a negative infinity and a positive infinity, which would be described as all real numbers if we wanted to make it into layman's terms. Okay, so I'm going to give you guys about a minute, minute and a half to copy that down. And then we're going to go to an example that makes us use them. All right, let me get back to my slideshow. Okay, and you can see that we're on example 2 for interval notation. This occurs on page 14 of the PDF. So it says, write that x is greater than or equal to -2 and less than or equal to and -12, or 12, sorry. X is greater than or equal to -2, but x is also less than or equal to 12 using interval notation. So once again, since we have the equal to element, it is encompassing -2 and 12. So we would want to describe this with using brackets. Okay, and our answer would be a bracket -2, because that is our lower number, and then bracket -12, stating that x falls within those, and since we have the bracket, it encompasses -2 and -12. Go to example 2B on page 15 of the PDF. Says write x is greater than -4 using interval notation. So as the last one, we were limited, we were bounded. They gave us -2 and they gave us 12. This one, they only give us 1, so we are unbounded, right? And it is also saying that it is not equal to. So in this case, we're going to use two parentheses. We're going to have parenthesis -4 showing the lower end of our interval. And then we should have a positive infinity because x is greater than -4. And we can't approach infinity because it is on the highest number imaginable. So our interval is parenthesis -4, comma, in positive infinity, parenthesis, to show once again that -4 is not encompassed within this interval. Okay, so it has to start at -3.9 or -3.99999. It just never can touch -4. Okay, it's very helpful when you're using these to describe domain and ranges of your functions. It makes it very quick, very easy using the interval notation. Okay, C says write x is less than 3 or x is greater than or equal to 54. So in this case, we want to decide which is our high number or our top end of our interval, which would be 54. And then 3 is going to be our low end of our interval simply because 54 is greater than 3. You can see that next to 3, we're going to have a parenthesis because it is not inclusive. But next to 54, we're going to have a bracket. Okay? Does anybody have an idea of why they use the union sign? Okay, you can see the answer that they've given us is parentheses, -infinity to 3 parentheses, union with 54 to a positive infinity. And that is presented because we have the element of or. This one isn't an interval where we have numbers that are less than and numbers that are greater than that aren't included. This one starts low from -infinity to 3, but then we go from 3 all the way to 53.9, and those numbers are not included in this interval. So then we pick it back up at 54 and extend to a positive infinity because those are the remaining interval or sets of numbers that are included within this interval. So or typically always means union. Could also be described as an and. So guided practice says write x is greater than 5 or x is less than -1 using interval notation. So if we work from our bottom answers up, the answer D has a -infinity with a bracket to a -1 with a bracket, and the union with 5 not included all the way to positive infinity. But if we look at it, that doesn't really fit because one, they're using brackets when we shouldn't have any elements. We should only have parentheses in this one. Looking at C, it says -1 to 5. Okay, so that's inclusive of -1, 0, 1, 2, 3, 4, 5, which would be correct for x is, which would be incorrect for both elements of our bound. Looking at B, it goes from -infinity to a -1 with a bracket. Once again, this answer can't be there because we are dealing with greater than or less than, not representing equal to. So from the process of elimination, we found that our answer has to be A, -infinity to -1 with a union of 5 to a positive infinity. Okay, so you can see how these help using the domain. It allows you to exclude numbers and include numbers very quickly, very easy, without having to list them all out and saying that x does not equal them. Okay, so that brings us to our next key concept, a function. Function f from set A to B is a relation that assigns each element x in set A exactly to one element y in set B. So in set A, you have all of your dependent variables. In set B, you have all of your dependent variables. So A is independent because they're the x values. B is the dependent. Also, you could refer to set A as the domain and set B as the range. And looking at our mapping there, you can see that 1 maps to 6, 2 maps to 8, 3 also maps to 8, and 4 maps to 9. Most people would say that this doesn't work because 2 and 3 map to the same y value. Understand that that's not a requirement of a function. It's only that each x value is independently assigned a y value. So that when we plug in 2, we better get 8 every time. And when we plug in 3, we better get 8 every time. So our graph just kind of comes up, then it levels out, and then it comes up again. You'd also see overlapping y values when dealing with a parabola. Okay? So it's not the y values that we're worried about, it's the x values. And in order to be a function, it must pass the vertical line test. So it says a set of points in the coordinate plane is the graph of a function if each possible vertical line intersects the graph in at most one point. So you can see the relation that they've drawn off to the right. If we were to draw that red line through each one of those blue dots, they would only touch the relation one time, or it would never touch more than one blue dot. So identify relations that are functions. This is probably the hardest way to look at it. One of the easiest ways to look at it is a graph, because we can draw our vertical lines pretty quick, pretty easily. Using a mapping or a table, we're given the x values. Here we got to kind of infer. So it says determine whether a relation represents y as a function of x. It says the input value x is the height of a student in inches, and the output value y is the number of books that student owns. Okay, so basically it's saying if you're 5'6", you're only going to own these books. Well, you can see that the number of books that you own or the type of books that you own has nothing to do with your height. Right? Any individual can buy multiple books. So since they're not reliant upon each other, this can't be a function. And that's because there's more than one y value or more than one book for any x value. Okay, so that's because it's a personal choice, personal option. I dare say that that's not even a relation. Okay, so B, determine whether the table represents y as a function of x. So you can see that this one's going to be a little bit easier because we actually get to see our x values, we get to see our y values. Okay, and we want to pay attention to make sure that we don't have repeating x values that have a different y value. And you can see in this case, it's broken it twice. Our first x value is 1, and we get the output value of -1. Our second one is again 1, but then we get a separate y value as 1. It would be a function if 1 only mapped to -1 for each occasion that we were to plug it in. You can also see that it's broken at 4 because 4 maps to -2 and to 2. And our last one, 9, is -3. So if we were to plot these points on an xy plane and we were to draw a vertical line on the x value of 1 and the x value of 4, we would touch our relation twice. So this would not be a function at all. Okay, now it says determine whether the graph represents y as a function of x. So we're given y is equal to x squared minus 3. It's a parabola. And we can use the grid lines as kind of a guide. We can look at it and say, yes, if I were to draw a vertical line that overlaps the grid lines, I'm only going to touch my relation one time at any given x value, so this would qualify as a function because it passes the vertical line test. Okay, here we got to do a little bit of algebra. Okay, it says determine whether x is equal to y, 3y squared represents y as a function of x. So I'm just writing it down. Help if I had a good marker. I think my cohort class is stealing my markers. Yeah, I'm blaming it on you guys. Yes, thank you. X is equal to 3y squared, and it wants us to represent y as a function of x. So the first thing that we're going to do is we're going to algebraically solve this. You can see it's up in the top right corner, and we're going to try to isolate y so that y is in terms of x rather than the opposite way around. So the first thing we're going to do is we're going to divide by 3 on both sides. And we're going to have that x divided by 3 is equal to y squared. And then we have to take the square root to eliminate y squared. So we get y by itself. Okay? And what we're going to end up with is plus or minus the square root of x divided by 3 is equal to y. And right now, we have enough information to determine that this is not a function because we have to bring over the element of plus or minus when we are taking the square root of something. That's because if we're taking like the square root of 9, negative 3 squared equals 9, but so does also 3 squared. So we add that plus or minus. So at this stage, we can declare that this is not a function. Oh, let me get, come on, thing. Work with me. Gotta love technology. So here they're walking through and solving. They take the square root. And you see plus or minus x says this equation does not represent y as a function of x because there will be 2 corresponding y values, one positive and one negative for any x value greater than 0. So if we let x equals 12, plug it into our equation, 12 divided by 3 is 4. So y would equal plus or minus the square root of 4, which would be plus or minus 2. Since there's more than one y value for each x value, it does not pass the vertical line test. Okay, here's our guided practice. Determine whether 12x squared plus 4y is equal to 8, and does it represent y as a function of x? So in this case, we'd do the exact same thing. We'd try to isolate y. So we would subtract 12x squared from both sides, and we'd be left with 4y is equal to a negative 12x squared plus 8. And then we would divide by 4 to isolate y by itself. And we would have y is equal to a negative 12x squared plus 8 all over 4. Since there won't be any element, or since each one y value for each x value, this would be a function. But once again, we got to solve it algebraically first. Okay, so here we get down to the meat of the chapter as finding functions. This comes from function notation, okay? And you can see that it says that f of x is equal to x squared minus 2x minus 8. And it wants us to find f of 3. So when you're dealing with function notation, we have to treat it as whatever we place into the parentheses, or whatever the book gives us into the parentheses, we're going to plug that in for each and every occurrence that we see x. Okay, so f of 3 is really equal to 3 squared minus 2 times 3 minus 8. Then we would carry out our order of operations. 3 squared is 9. Minus 2 times 3, which is 6, minus 8. And then we would combine all of our terms because they're all like, and we have no more elements of the variable. 9 minus 6 is 3 minus 8. So f of 3 is equal to a negative 5. Okay, so when it comes down to function notation, it's just a matter of plugging it in and replace each occurrence with x with what is given inside our parentheses. So f of 3 is equal to a -5. Is that a good one? Okay, so here's the second to last example that I'm going to show you. And this one requires a lot of work. You can see that they've given us f of x is equal to x squared minus 2x minus 8. And they want us to find f of 2a minus 1. So the first thing that we have to do is we have to replace that binomial for x anytime we see it. So the first one is 2a minus 1 squared minus 2 times 2a minus 1 minus 8. Okay, this one is very labor intensive, and that's because they've given us a binomial. Let me stop the share so you can see me actually work through it. Okay, so we're dealing with this. Our -8 is going to stay, it's our constants, pretty easy. For 2 times the quantity of 2a minus 1, we have to use the distributive property. Okay, where we plugged everything in, we have to use the distributive property. Here, we have to FOIL. Okay, so we have 2a minus 1 times 2a minus 1. And like I said, we're going to FOIL it out. 2a times 2a is 4a squared. 2a times -1 is a -2a. -1 times 2a is a -2a. -1 times -1 is a +1. Okay, for our interior term, we're going to use the distributive property. So it's -2 or -2 times 2a minus 1. So -2 times 2a is a -4a. -2 times a -1 is a +2. Our constant remains the same. So now we're at a stage where we can combine like terms. Okay, we've done all of we FOILed the first term because it was a binomial that was squared against itself. So two binomials multiplied against itself, always have to use FOIL. We distributed our -2 into 2a minus 1. That's where we got -4a plus 2, and our -8 stayed the same. So going through looking at like terms, there is no other element of a squared, so 4a squared is going to stay. I have -2a, a second -2a, and a -4a. Those are all going to combine to a -8a, and now those are gone. And now I'm left with a +1, a +2, and a -8. So 1 plus 2 is 3, minus 8 is -5. And our answer is 4a squared minus 8a minus 5. So the key thing when you're dealing with function notation is whatever appears in the parentheses, we plug in for the variable. It'll typically always be x. Okay? I was going to talk about piecewise functions. Well, I'm going to save that for the next class. Like I said, they're handled just like this. They're pretty simple, pretty easy, but they are a matter of, they're not on this book assignment that you're going to have today. So I'll cover those on Wednesday.